Welcome back, folks. We're starting something new today. We've been looking at two different types of steady states. We've been talking about DC, everything's a constant, nothing changes. Everything sums to zero, it's nice and easy. The other steady state we've been looking at is the AC steady state, where the phasor representation doesn't change. So even though it's a voltage that's varying, we still have a representation that's a constant. That's not what's always happening in a circuit. A lot of times we're moving between two different steady states. We call that a transient condition. So we're going to start to look at some of the simpler transient conditions. We're kind of reaching the end of this class. And if you want to continue to study transient conditions in circuits, you can do that in some of the courses that come after this one. So we're going to deal with only the simplest of transient conditions, but there's some good things to learn. It is worth talking about them here. We want to have some idea when we walk away from this how to write an expression for the voltage as it moves through this transient condition. And we'd also like to have some idea of how long it takes the circuit to move through this transient condition. So that when we have a network cable and we're switching it from a 0 to a 1, well, how long is it going to take the receiver on the far end of that transmission cable to see that same transition between the two states? Okay, that's the example that comes to mind right now. We got to dig into some of the math. I'm still going to try to get down to Ohm's law, KVL, and KCL, but I'm also going to give you some techniques that will help you analyze these circuits, write these expressions quickly, and hopefully have a good understanding of the different things that influence the timing of the transient condition. Okay, so we're going to look at 4 circuits, and I'm going to go through a fair amount of math. And hopefully you can stick with me, but what we're going to get down to is the form of the solution in all 4 cases. And we're going to use this form of the solution, which we can generalize for these 4 circuits, and we're going to use that to do analysis. Okay, so 4 videos, 4 circuits, all of them, what we're getting to, the payoff is the form of the solution at the end. So let's look at our first circuit. We have a capacitor and a resistor. That's it. If I were to find this in the wild, as if I find circuits in the wild, I would assume that there's no voltage across this capacitor, but what we really want to do is say, what if there was some voltage across the capacitor? How long would it take to discharge, and what would it look like? Okay, so this is our discharging capacitor. And we're going to tackle this the same way we have in most of our other problems. We're going to use some method of analysis to write a system of equations. If I use nodal on this one, I'm going to save myself a little bit of a headache. So I already have the ground labeled, and I have the one reference node. I have the one non-reference node labeled. Okay, both of these are passive, so we can label our current directions like that. And then we start writing. Okay, so we have the current leaving. Let's see. We have the current leaving this node, and it's going down through the capacitor, right? So it's going to be negative IC of t. I'm going to start dropping the functional notation. It's going to get a little cumbersome. And this one's also leaving, so it's negative IR of t. And that's all the currents going in and out of that node. So KCL still holds. Just because it's a transient, just because we have different components, it's still a KCL equation. That's going to be the starting point of the wall of math I'm about to give you, but I'm going to try to break it down slowly so you can stick with me. Okay, now if I multiply both sides of this by -1, we can write it that way, and it's a little cleaner. I use the negatives because that matches the way that we had the signs down there. Okay, so the current through the capacitor, we're going to relate that to the node voltage using the capacitor equation. right? And the current through the resistor, just like we did in Ohm's law, in nodal analysis, we're going to use Ohm's law. Okay, and that's going to allow us to rewrite this equation in terms of the unknown node voltage. And that's all we were doing with nodal analysis. We just have to use the capacitor equation in one case here. So we have IC of t is equal to C dV of t over dt. Okay, and for IR of t, that one's just going to be the voltage of the capacitor, Vc of t over R. Okay, V equals IR, so I can move the R up there, and it's just Ohm's law. That's what I'm going to plug in here. So let's say this one's getting plugged in for that, and this one's getting plugged in for that. Okay, what's that going to look like? That's going to look like this. I'm going to bring it down over here. C dV, forgive me if I drop the of t, it's just more writing. And we know that lowercase v is time transient. So C dV dt plus Vc, over R. Okay, I should have a subscript of C in there. All right, and that equals 0. Okay, this is where the diversity, the academic diversity in our classroom, could cause a split in how we approach this. All of you have taken at least Calculus 2. Some of you have taken DiffEq. Some of you have taken modeling in the mechanical engineering program. And what you're looking at here is a first-order differential equation. So some of you know what that is, and some of you haven't taken that class yet. But what we're trying to do is find a solution. We're trying to find an expression, Vc, that is going to make this formula be true. So this is our first-order DiffEq. So because some of you haven't had a formal DiffEq class, what I'm going to do is develop that solution, the expression for Vc, using a method that focuses on integration, since all of you have taken Calc 2. So I'm going to try to separate and integrate to find the solution. In order to do that, I got to shuffle things around a little bit to make this work out cleanly. So I'm going to take R, I'm going to multiply both sides by R, and that's going to bring, whoops, I wanted white. That's going to bring R up here as it distributes to both of these terms. And it's going to get it out of the out of the denominator over here. Okay. So that looks a little better. These are constants. I'd like to try to keep them together and just treat them as constants, as one constant if I can get away with that. And it's actually a pretty cool constant. It tells us something about how this circuit's going to behave, R times C. And we'll see what that is, hopefully at like 4 or 5 videos from now. But we just want the form out of this one. Okay, bringing this term over, RC dVc of dt, right, negative Vc. Okay, so we subtract it from both sides and we get a negative on that side. Let's see, now we want to get, the goal here is to get all of our T's over on one side and all of our Vc's over on the other side, if we can get away with that. So we can actually break this up because this is the derivative. It's akin to the slope. If you haven't really dug into that, hopefully that comes back from calc for you. So I'm going to bring dt up, okay, and leave dvc there, negative vc dt. Okay, so I almost have all of my, t's over here. I need to get all of my vc's down over here. So I really just need to divide by that. I'm also going to bring my RC over if I can. It's going to make my life a little easier. So I'm going to end up with negative 1 over Vc dVc. And I'm going to, oh, I don't want that negative. Okay, I'm going to leave the negative there. I'm going to have negative 1 over RC dt. All right, and that's in good shape. I have all of my v sub c's on one side, and I have all of my t's on the other, and really all that's left is to do some integration. So if I integrate both sides, okay, we can get to where we're going. So we want to know what's happening when the cap starts to discharge. So we're going to call that T0, T equals 0. Okay, so that's going to be 0 there, and we want to know, we want an expression as a function of time, so we're going to call the upper limit of integration capital T, and then we have to be careful not to confuse that lowercase t with this lowercase t. So we're going to swap this one out. We're just going to make it a different variable so that we know what's going on. We'll call that one tau. Okay? On this side, we want the limits of integration to match, but they need to be similar to the voltage, right? So this one's going to be the voltage across the capacitor at t equals 0, and this one's going to be the voltage across the capacitor at t seconds. Okay, and those are the integrations we have to do. We got to do both of those integrations and then solve for Vc of t, because that's ultimately what we're trying to find, is an expression for this variable right there. Okay, so you got to remember your integration. So the integration of 1 over the variable of integration is, hopefully you recall this. If not, please go look up an integral table. But that is going to be the natural log. Okay, so we're going to have the natural log of Vc. Okay, and we're going to use tau there. And we're going to evaluate that between our limits of integration. So from Vc of 0 to Vc of t. Okay, so that's the left side, getting there. And then the right side, if I'm negative 1 over RC, negative 1 over RC is a constant, right? So if I'm just integrating, and it's an empty integral, it's really a coefficient of 1 in front of dt, then, or d tau in this case, then I'm just going to get tau back, right? So I'm going to end up with just a single tau there, doing that integration. Limits of integration on that one, we're going to evaluate it from 0 to lowercase t. Okay, we got to plug some of these in since we have definite integrals. So I'm going to plug this one in, and then I'm going to subtract the same thing but with this plugged in. So it's going to be the natural log of Vc of t minus the natural log of Vc of 0. Okay, that's the left-hand side. Working on the right-hand side, we're going to end up with, let's see, I'm plugging in for that, so it's going to be negative t over RC minus a negative 0. It really doesn't matter. It's going to end up being positive. Okay, 0 over RC. So this term drops out. We don't really need it, right? That goes to 0. It doesn't matter what the denominator is. Okay, so the right-hand side is looking manageable. It's pretty good, right? Negative t over RC. I can live with that. We've got some logarithms here. Go back and look up your log identities for this one. Some of you are going to know it. I usually ask in class and say, how can we reduce that and make that a little more manageable? And we end up with, we end up with the natural log of Vc of t over Vc of 0. Okay, so if we have a quotient in here, we can break it up this way, or vice versa. So check your log properties. That one is super useful right now. Negative t over RC. That's still our right-hand side. We're getting closer, folks. Okay. Let's see. We want to solve for Vc of t. So I've got to get that by itself, and I got to get it out of the logarithm. So in order to do that, I got to get rid of the natural log. I'm going to make both of these sides exponents of the natural constant E. All right, that'll cause that to drop out. Okay, and I'll just be left with this over here. So we get VC of t over VC of 0 equals e to the negative t over RC. Okay, almost there. We just got to get rid of that VC of 0. That's our initial condition. So whatever voltage is on the capacitor when it begins to discharge, we just need to multiply both sides by that. So we get VC of t equals VC of 0 times e to the negative t over RC. All right, and that's what we were looking for out of this video. So if we know the resistance and we know the capacitance, then we can figure out what the voltage is at a given time. We have to know the initial condition as well. Okay, where is it starting from? This is the first form. We're going to look at these, we're going to plot them, but I want this form, I'm going to save it, I'm going to cut and paste it into a future video, or maybe just rewrite it. This is the first one in that standard kind of general form for all of our equations that we're going to find for the discharging capacitor, charging capacitor, discharging inductor, charging an inductor, and we're going to figure out how to use that to our advantage to find these expressions quickly. Okay, so I'm breaking it up because I'm already at 16 minutes. That's plenty of time. How did this capacitor get charge on it in the first place, and how long did that take? That's what we're going to do in the next video, and it's going to get us closer to our goal of analyzing all of these. So stay tuned and good luck.